Okay, so let's continue this plasma oscillation physics that we introduced last time. So as we derived last time, we found this plasma oscillation frequency, omega p, which is a function of average electron density of your system, and also some universal prefactors. But we have a few remarks to be made after we derive this plasma oscillation frequencies. And we have mentioned a couple of remarks last time, but let me just emphasize these remarks once again here. So the first remark is that the plasma oscillation phenomena in metals is actually a collective quantum phenomena. So there are two key words. The first one is collective. The second is quantum. So by saying collective motion, what I mean is that all the electrons involved in this density oscillations, as we will see in just a moment, right there, that it involves all electrons near the Fermi surface, and they oscillate in the same frequency. So it's a collective many-body phenomena, and this is a quantum phenomena because, of course, we find this plasma oscillations through the solving for Heisenberg equation motions. And we don't have that Heisenberg equation motion in classical systems. So, and this is precisely the second remark for the classical gas, because the commutator between the Hamiltonian of a classical electron gas and the classical electron density is actually zero. So that's is well known in your classical electrodynamics. There's no non-trivial commutation relations between the Hamiltonian and electron density in the classical system. As a result, if you solve for the Heisenberg equation motion for the classical electron gas, you'll get nothing, because this density is actually a constant motion. So there's no such a thing as electron density in the classical gas will oscillate, because the commutator vanishes. And however, we do have this analogous plasma oscillations in the classical electron gas, but only in the presence of external AC fields. Remember, in your EMN, if you apply the AC alternating current or alternating electric field on a soup of electron gas, then they will oscillate together as a sort of classical plasma. But here we are talking about spontaneous collective phenomena in quantum systems. So we don't need to apply any external electric field or magnetic field to actually induce such a collective motion. So quantum mechanics allows such plasma oscillations. But in classical electron gas, we do need the AC field to actually induce such a plasma motion for electrons. So this is a huge difference between the classical plasma phenomena and a quantum mechanical spontaneous collective quantum phenomena. Okay, so our analysis is probably the only way that we could really analytically understand such a collective motion. So number 3, this quantum plasma oscillation phenomena involves all electrons near the Fermi surface, as I just mentioned in the previous remark, that it is a many-body collective motion which involves all electrons near the Fermi surface. So in particular, near the Fermi surface, electron density actually oscillates in a very long wavelength. Okay, the period is really, really huge because the moment of transfer Q is small. So everybody stands together. So those electrons near the Fermi surface, they could actually oscillate in the same frequency. collectively with a very large wavelength. So number 4, remember we made such an assumption that we could neglect this kinetic energy term if this condition is satisfied. And I mentioned that it is easy to satisfy this in ordinary metals because omega p is large and Fermi velocity is not small, but finite. So and a q is a momentum transfer that we can tune. So we could certainly consider a situation where q squared is much less than this omega p squared divided by vf squared. But we can also consider the q, which is much larger than this so-called critical value of a q squared. So as I mentioned previously, that for a large momentum transfer, this kind of density fluctuations is actually a high energy single electron hole pair phenomena. Remember that, right? So if I excite this electron hole pair from the inner core electron states well below the Fermi surface, then we need a very large momentum transfer to realize this kind of a high energy electron hole pair excitations. And this occurs only when q momentum transfer is much larger than this critical value of qc. But for low momentum transfer limit, when q is much less than qc, and we find that this is controlled or dominated by the plasma oscillation physics. So this thing is actually really making this distinction between the Hartree-Fock theory and this approach that we used to get this plasma oscillation in the basis of the density operators. So let me just illustrate the relation between the screening and the plasma oscillations. Okay, so we will derive the screening phenomena in just a moment, right after these remarks. So this diagram illustrates the relation between the plasma oscillation phenomena and the single electron hole pair phenomena in terms of the value of this momentum transfer, either it's below or above qc. So based on this, we could separate or divide the Hamiltonian for metal into two parts, especially the potential energy part, because we know that there are two different phenomena are here, depending on whether this momentum transfer is larger than qc or smaller than qc. So we could divide this potential part of the electron gas, Coulomb interacting electron gas, in terms of short range Coulomb interactions, where this q is actually larger than qc, or this kind of a long range Coulomb interaction, whereas q is actually smaller than qc. So and then we could argue that the total energy, if we consider just the long range part of the Coulomb interaction, which means that in the plasma oscillation regime, then indeed the energy associated with this plasma stays in the t equals 0 limit, where we could imagine that we consider these plasmas of electrons reach to the ground state, and we can calculate this total energy of this long-range part of this Coulomb interaction, which leads to the plasma physics. And this energy, we'll see in just a moment, that is smaller than the Hartree-Fock energy, in the same region where we consider a very long-range, Coulomb interaction. So the reason why this plasma oscillation regime is a long-range Coulomb interacting regime is because Q is actually very, very small. When Q is small, this immediately tells us that this, the range of this Coulomb potential in the real space is actually large, right? Vice versa. So if you consider very large momentum transfer limit of the Coulomb interactions, and if you Fourier transform this, this is actually dominated by this short range part of the Coulomb interaction, meaning these electrons actually are very, very close to each other. Good. So let's just compute this potential energy and the kinetic energy of such plasma oscillations. Remember, this plasma oscillation is nothing but the harmonic oscillators, right? Because this density operator oscillates in times in this kind of a quadratic fashion in the Hamiltonian. So this has the same form as a simple harmonic oscillator. And we know that very well in your general physics that if we have charge oscillates in a harmonic oscillator fashion, then we can very easily calculate this potential energy and kinetic energy. So in quantum mechanics, we can also do so. And from the experience of the simple single harmonic oscillator problem in quantum mechanics, you know how to actually extract this zero temperature potential energy. And here, this is nothing but half of this 0 point energy, epsilon 0, which is 1/2 h bar omega p. Likewise, the kinetic energy of such a charged harmonic oscillator motion in quantum mechanics shows exactly the same value at ground state, which is again 1/4 of h bar omega p. So if you add these two values together, you get a total energy in the plasma regime, and you can compare with our earlier predictions by Hartree-Fock approach, and you will find that this part of energy is actually smaller for a plasma phenomena than that's predicted by the Hartree-Fock. So in other words, the plasma physics is actually more stable than the Hartree-Fock ground state. And we will see in just a moment that this kind of plasma oscillations will lead to the screening of a Coulomb potential. And this reinforces our earlier statement that this kind of a density operator is actually a correct starting point because it leads to a more stable ground state compared to the Hartree-Fock, and the Hartree-Fock approach failed to give a reasonable description of many quantum effects of metals. Okay, so let's take a short break. When we come back, we could start to derive this quantum version of the Coulomb screening effect. Let's continue. So before we study the screening of a Coulomb interaction, so let's just discuss detection of these plasma oscillations in the real experiments, just to actually end this part. As I mentioned earlier, this plasma oscillation phenomena is a real quantum mechanical phenomena that you could see and observed in the real experiments. So this is an example of such experiments that has been done many years ago. So the setup is this, showing this in this diagram. Here we emit some electron beams with high energy, and the energy of electron beam is about 20 keV, which is a really high energy electron beam. And this electron beam hit the target, and target is aluminum thin film, which is about that range, 200 or 300 nanometer in space. And this electron will actually hit the electrons in the aluminum thin film. So the external electrons will actually interact with all the other electrons in the thin film, and then finally these electron beams are going out of this thin film, and you could detect initial energy and the final energy of such electron beams and their intensities. So you could plot this intensity versus the energy difference or energy loss between the incoming electron beams and the final electron beam. And you can make a plot, and this is a typical plot of such electrons interact with the plasma oscillations in your electron sea of ordinary metals. And in the case of aluminum, you can see very clearly that there are periodic peaks in the integer values of energy difference between incoming and outgoing electron beams divided by so-called energy difference delta E, which is about the single plasma energy, h bar omega p. If you calculate the plasma oscillation frequency for aluminum and multiply by h bar, you'll find this is about 15 electron volt. But experimentally, we don't know about this plasma physics. We simply just observe such periodic peaks, and you could rearrange your data in such a way that the x-axis is plotted in terms of the energy difference EI minus EF divided by the some unknown quantity delta E. And if I could adjust the value of delta E in such a way that the peaks appear only at integer value of x-axis. And such delta E obtained experimentally for this aluminum case is about 14.8 electron volt. And you can see that experimentally I don't know about this plasma physics. I only see phenomena, and I only observed such a periodic peaks. And if I normalize my energy loss in the proper way, and I can see that delta E is about 14.8, which is very close to this plasma oscillation energy. And this is the direct proof that indeed there is no other way to explain such periodic peaks in this detection of electron beam. So only explanation is this is the plasma oscillation physics. And delta E observed experimentally is really, really close to a calculated h bar omega p. And so this is the experimental observation done a long time ago to demonstrate that plasma oscillation is really there. So, but how to actually interpret or understand this kind of a periodic peaks in the density plots? Well, this will actually link to the earlier notion that we mentioned many times, that in many solid-state systems we can find some kind of a quasi-particle excitations. Here, the plasma oscillations, which is derived from quantum mechanics, can be considered as an example of a quasi-particle excitations, because as you can see that this h bar omega p can be observed or emitted by these electron beams and in the integer multiple times. For example, here I plot 3 h bar omega p coming along in between this EI and the EF of such an electron beam. So the incoming electron beam carry very high energy, but then when these electrons pass by all the other electrons in the soup of the plasma oscillations of the aluminum thin film, then this electron beam loses energy. Okay, but how much energy that electron can actually be dissipated? Well, you can actually count how many plasma oscillation frequency associated with the plasma energy, which we call this plasma, as a quantized energy of such plasma oscillations in quantum mechanics. And this is an example of a quasi-particle. The quantized energy for plasma oscillation physics is called plasma. Okay, and the plasma carry the quantum unit of energy of h bar omega p. Okay, and if I have 3 h bar omega p in between E and EF, which means that the electron beams loses energy. Say, how much energy does it lose? It loses 3 h bar omega p, and therefore this corresponds to such peaks here. Okay, so of course the electron beams do not necessarily interact with the plasma. It can directly pass by and pass through this thin film of aluminum, and so you get 0 peaks at 0 here in the x-axis. and then you get the peak at integer values 1, 2, 3, 4. Okay, so these integer values correspond precisely the number of plasma energies that electrons have lost. All right, so electron can lose, say, 0 plasma energy, or 1 plasma energy, or 2 plasma energy, or 3 plasma energy, or 4 plasma energy, and so on and so forth. Of course, the more plasmas involved in this energy loss, the less the probability that this intensity will show. So you can see that the peak gets shorter and shorter, and the probability of such a multiple, many plasma, energy involved is really, really low. Okay, but the first few plasma absorption or emission processes, is actually are noticeable. Okay, so this probability or intensities are really noticeable and detectable, and this is really what happened in the real experiments. So let me just make the list similar plasma energies for lithium, sodium, and potassium. So you can see that the observed plasma energy are very close to, reasonably close to the calculated value of the plasma energy. So this is the predicted of calculated plasma frequency omega p squared, and if you plug in this reasonable estimation of this average density or plasma frequency, and you get the value of this h bar omega p. Okay, so so that concludes the plasma oscillation phenomena. So now let's turn to the very important final sections of this part, which is the derivation of the screening of a Coulomb interactions. Remember, last time we derived such a Thomas Fermi, a wavelength or Thomas Fermi wave number semi-classically, but here we will derive the same screening of a Coulomb interaction as we did before, but here we do it purely quantum mechanically. So we use pure quantum mechanics, and we don't consider any classical electrodynamics in this derivation. And what we will do is, again, we consider a response or feedback effect to the external potential U, and that external potential is induced by, remember, some kind of a charge disturbance or test charge. Suppose there is a test charge or somewhere in this electron gas, and then this will induce some kind of a charge disturbance, delta rho, and this delta rho will lead to some kind of a potential variation or potential fluctuations, which is given by this potential of this charge disturbance multiplied by the charge disturbance, delta rho, and delta rho at the finite moment transfer Q here represents such kind of amplitude fluctuations of this charge disturbance, and in the second quantized fields, it can be represented by the sum over P, C dagger P plus Q, Cp, and plus C dagger P minus Q, Cp, which is the real part of this complex operator rho of Q plus rho dagger of Q. So this amplitude fluctuations represents this, the size of the magnitude of this charge disturbance is like a electron charge here, but this electron charge is not a unit electron charge, but a charge disturbance. So this charge disturbance is actually the amount of the charge fluctuations were coupled to this potential U of Q, where U of Q is nothing but this form, 4 pi squared over q squared. Okay, so this is the total potential energy associated with the charge disturbance induced by the test charge or this charge disturbance delta rho. So we will consider the situation where V and U are both very, very small, and we can consider this kind of terms U plus V as a small perturbations, and we performed perturbation theories in quantum mechanics, and we expand this this kind of states, the true ground state of this full Hamiltonian in terms of the unperturbed eigenstate H0, and then we treat this U plus V as a small quantum mechanical perturbations. Okay, so let's take a short break, and when we come back, we will continue analyzing this perturbation theory to get the screening of the Coulomb interactions, and in particular, we start from the correct operators, which is the electron density operator. Let's continue. As I mentioned just a minute ago, we will derive this Coulomb screening effect based on these density operators. In particular, we are trying to consider the kind of mutual effects of this electron static potential in the presence of external charge disturbance, and that charge disturbance is going to create some kind of a variation of charge density over space, so which corresponds to the finite momentum transfer component of the the density operator. But we know that in addition to the this kind of a electron density disturbance, there are already many electrons or charged particles distributed in the system, and they have this Coulomb potential between them. So then the whole Hamiltonian is just the sum of all these different aspects of the Coulomb potential and plus this free electron kinetic energy part. So we have three terms in the Hamiltonian: H0, which is a free electron gas, and this potential V, which comes from the internal electron potential of a Coulomb form, and U delta rho, which is induced potential electron static potential due to the presence of this charge disturbance. And this charge disturbance, of course, can be induced by some kind of a test charge or density fluctuations. Remember, we talk about this electron hole pair excitations many times. So whenever we actually excite such a low energy quasi-particle electron hole pair near the Fermi surface, then the electron density changes. Okay, because now we actually lose one electron inside this Fermi surface, but we have one more excited electrons out of the Fermi surface. So in other words, these excitations will change electron density, and such a kind of a plasma oscillation of charge could be described by this kind of a spatial disturbance of the charge density delta rho. And in Q space, this is given by delta rho of Q. So delta rho of Q multiplied by this U of Q, which is nothing but the Coulomb potential, and this product is nothing but the electrostatic potential due to the charge disturbance. And so we will study the mutual inference between U delta rho and V of Q. So the presence of the V will affect this U delta rho, and vice versa, the presence of a U delta rho will affect V of Q. So this is called the feedback effect. Remember, we discussed this feedback effect when we solved the Poisson equations semi-classically combined with the Schrödinger equation, right? But here, we do it quantum mechanically, purely. So the way that we do this is based on this Rayleigh-Schrödinger perturbation theory in quantum mechanics, where we consider both U and V are simply just small perturbations. Of course, we will come back to this assumption later, but let's just assume that both U and V are small enough, and we could apply this perturbation theory in quantum mechanics that you are already familiar with, I suppose, in the sense that unperturbed Hamiltonian H0 shows the eigenstate phi with the eigenvalue epsilon 0. But once we include this small perturbation, we don't know this the eigenstate of the full Hamiltonian is, which is psi, and we don't know the eigenenergies. Okay, but the nice thing about perturbation theory is that we can expand around this what we know. So this is known, the ground state of the unperturbed Hamiltonian, but psi is unknown. So we can expand the known results to give approximation for this unknown eigenstate of the full Hamiltonian. And we do it order by order in orders of the small perturbation U plus V or square of U plus V. So, and this is the approximation, or this coming out of the perturbation theory, and which I leave this to you as a homework exercise and try to derive it. And this is something that you should know when you study quantum mechanics. So the unknown eigenfunction or eigenstate psi shows such a kind of a summation of all different terms. In the first terms, of course, the unperturbed eigenstate phi plus some small corrections, and the small correction have infinite number of terms, because here I just include the first order term, but I neglect there should be a second order term, but due to limited spaces I don't bother writing it down. Plus the higher order term, the third order term, and the fourth order term, and so on and so forth. So it contains infinite number of terms in orders of the small perturbation U plus V. The zeroth order, of course, is a non-perturbed state, and this first order is linearly proportional to the small perturbation U plus V, and the second order term is proportional to U plus V square, and so on and so forth. Okay, so we will start from the simplest two terms, which is the first order and the second order term. And we will add higher order terms later, but we could just study the first two terms. Okay, and here this 1 minus phi phi projection, this is a projection operator which project out of the ground, outside of this unperturbed state. You project this result out of the unperturbed state. Okay, so I leave this to you as a homework exercise to show that indeed we have such a factor here. Okay, and this epsilon 0 minus h0 to the power of inverse is actually this kind of energy denominator, but we could define this operator. H0 is an operator, epsilon 0 is the eigenenergy of the H0, and 1 over epsilon 0 minus H0 is another well-defined operator which gives you this eigenvalues of this 1 over epsilon 0 minus epsilon k something. Okay, so as a intermediate energy denominator for intermediate states. Okay, so I have no time to derive such a perturbative expansion, but you could do that. So let's just expand this Rayleigh-Schrödinger perturbation theory up to second order in U and V. And so the zeroth order term is this. And the first order term, we could just divide this u plus v in terms of the v only term and u only term. And we focus on all the terms that involves u, because we would like to study the effect of the v on u. So the second order term, is summarized in 2 lines. We have v and u multiply together, but v comes first and u later, right? Of course, we have the other term which we switch the order between v and u, so that we get u in the middle here and v appearing at the very last. Of course, up to second order term, we have 2 energy denominator, epsilon 0 minus h0 inverse, appearing in this expansion, and we could keep expanding up to infinite number of orders in u plus v, but we just cut it here up to second order, and we try to collect all the terms containing a factor of u, okay? Because that's the effective total potential, right? So remember, in the presence of both u and v, so they are mutually influence each other, in the sense that in terms of the perturbation theory, this effective potential, u effective, is no longer just the bare u itself, but it includes all the higher order terms that come from this perturbation, perturbative expansion, and we should also take all the corrections into account to get the total effective potential, u effect. And that's u effect, of course, includes all this feedback effect, right? So the influence of v on u, so all this u effective expansion includes the bare or unperturbed potential u, but there are all the other terms that come from the higher order perturbations, and in particular up to second order we get v first and u later plus u first and v later. So that's the up to second order. Of course, you could keep collecting all this u effective from the higher order expansions, but let's just stop here for now, and we could go back to this higher order term later. So if I define this first order term as this term 1, number 1, and the second order terms, there are 2 terms, term 1 and term 2, which I call this number 2. So if I sum over the first order and second order terms, I get this right-hand side of this equation. But instead of I expand all the terms, instead of this, I simply just use u effective, okay, to summarize all this kind of terms, including terms influenced by the presence of v. So as I mentioned, this screening effect comes precisely from the so-called feedback effect, where we know that the presence of the u will affect the v and vice versa. So everybody influences everybody else, as I mentioned many times in the past. But we could just focus on, say, the effect of v on u, meaning we simply just collect all the terms that contribute to the u, and we define this as u effective, and we'll show that u effective actually follow this kind of a Yukawa decay, which cuts off this long-range Coulomb potential. And likewise, we could later collect all the terms involving v, and we could again define v effective. Again, by the same token and argument and derivations, we can show that v effective is also following this kind of a Yukawa type of exponential decay in long distance limit. Okay, so this approach actually shows the same spirit as we did via this semi-classical Thomas Fermi approximation, that the presence of this test charge will create or induce some kind of a charge disturbance, and the total potential should also include such a charge disturbance, and then we should solve these Poisson equations self-consistently, including everything. But here, we don't use this Poisson equation. What we applied here is nothing but this perturbation theory in quantum mechanics. So everything comes naturally from quantum mechanics. So the next thing we do is we collect U effective, and we try to analyze up to second order in perturbation what this U effective will do. Let's finish the first part of the calculation. So as I mentioned, if you sum up all these terms involving U and up to second order, we have two terms, the term number 1 and term number 2, and we can define this U effective like this. And in particular, the first order term is really trivial, which is just the U, but this, the second order term has two terms, which are non-trivial, and we will study these two terms one by one. And first, let's just focus on the first term, where V appears before U. Okay? In that case, we simply just expand all this operator of this term, which leads to a bit complicated 6 operator terms. Okay? So let's just repeat that 6 operator terms here, and we could analyze how this kind of electron scatters in the presence of this disturbance, and also in the presence of the usual Coulomb potential. So there are two scatterings. One is the U, where incoming electron carrying momentum P is scattered off by this U of Q, and then the outgoing electrons carry momentum P plus Q. So that's this first term. The second scattering is just the usual Coulomb interactions, which we already outlined and sketched this diagram before, that there are two electrons carrying momentum K and K prime, and these two states are destroyed, and instead this electron carrying momentum K after scattering becomes another electrons with momentum K minus Q prime, and the second electron initially carrying momentum K prime, and after scattering it carries K prime plus Q prime. But these two scattering processes are actually connected to each other, because we would like to actually evaluate this expression value of such a 6 operator terms. And so the way that we actually connect these two is the following. So we could actually connect or link the states, the initial states K, for the Coulomb potential term, the V terms, and link it to this P plus Q. And this K minus Q prime term in the V part could be linked to the initial states of the P for the U term. Okay? And this is as a possibility to actually make the non-trivial contribution to this expression value, because all the other possible scenarios will not lead to this non-trivial results. And we have two possibilities here to contribute to the finite result. The first one is when Q is the same as Q prime, and P plus Q is actually K, or P is actually K minus Q prime, or P plus Q is K. So in such a scenario, so the initial state P right here, and after the first scattering by U of Q, and it becomes another electron carrying momentum P plus Q. But in the first possibility, this Q is actually the same as Q prime. So P plus Q prime is the same as P plus Q, but this P plus Q prime is the same as K. All right? P plus Q prime is the same as K, so this is what we make the link by establishing this identity where P is actually the same as K minus Q prime, which is K minus Q. All right? So, and therefore, the outgoing electron, it's actually connect to the, this state, K minus Q prime, which is the outgoing states of the second scattering. So, and the remaining part is actually, trivial because this is K prime, this initial state, and the outgoing state is actually what? K prime plus Q prime, which is K prime plus Q. So now you could actually link this outgoing state on the right and initial state to the left because both states are states with momentum p. So you can actually link them together. Okay? And then you can actually distort this diagram in such a way that this is U of Q appearing on the top, and there's a bubble in between this bottom line and this U of Q. And this bubble contains two so-called propagators or electron states. One is state P, another is state P plus Q. And they move towards the opposite directions. And in the bottom, we have the incoming state K prime and the outgoing state K prime plus Q. So that's the first possibility. The second possibility is that Q is actually minus Q prime. So in that case, you get exactly the same diagram as this before. So let me just summarize. If I just analyze the first term of the second order term, which V comes first and U comes later, then I get to this 2 times sum of P 1/2 V of Q MP 1 minus MP plus Q times epsilon P minus epsilon P plus Q inverse sum over K prime U of Q dagger K prime plus Q C K prime. Okay, so let's stop here now for today. So next time I will start from this result, and we could analyze the second term, the second order in perturbation, and we sum up everything and we get the contributions for U effective contributed from both the bare U and the presence of the V terms. So I'll see you next time.